In this question, what did you say? We can find out the acid base neutralization point by either using a indicator, right, the endpoint, or we can use a pH meter. When you use a pH meter, that the it will be having a typical graph like this, right? This is the
Yeah.
pH, this is the NaOH, and this is the volume of the NaOH which perfectly neutralizes, right? But another way we can do is that any acid base reaction is exothermic in nature. So we add the acid, we take the acid, we add the base from a burette, and we note down the temperature which is going, right? We plot the temperatures like this. We plot the individual temperatures, right? Now
Yeah.
we will be missing this point, right? When the temperature is reaction is over, what happens? The temperature goes down like this, right? So we are
Yeah.
extrapolating this graph and we find out the volume of the NaOH which is being used to for the neutralization point. Done. So this is also the thermometric way by which we can analyze a neutralization reaction. Done this part. Uh, so one group of the student accidentally use a temperature probe rather than the pH probe. So this acid-base titration, HCl and NaOH. The volume of the NaOH given is what? 25 plus minus 0.05. Concentration of the HCl, we're taking this, right? We're taking this concentration, right? So
Yeah.
what we're doing, we are trying to measure the concentration. Can you tell me what is written over here? The volume of the HCl written over here, right?
Yeah.
Yes, yes. Can you go up a little bit? Thank you. Now over here, what they're saying that the graph is given over here. So what we do, we extrapolate this graph, right? The HCl which is used, right?
Yeah.
Extrapolate this graph. So exactly the neutralization happened at this, right? This is the point which happens, right? So 1, 2, 3, 4, 5, 6, 7, 8, 10. So this is what? This is 35, right? 35 it happened, right? Hmm.
Yeah.
35 centimeter cube of the HCl which happened. Now see, they'll be giving you questions of the, you get given the questions of the of the converting the absolute uncertainty to percentage uncertainty. I hope that you know that, right? This part you
Yeah.
know, right?
Yeah.
So this is the graph which we have to plot, or graph will be given. Usually the points won't be given. This, they are very generous to give you the end point over here, right? But usually it won't given, right? These two will not be given. You have to extrapolate the graph backwards and you find out the end point like this, right? Do this. Go up, go up. Can you do this? With the
Yeah.
percentage
Yeah.
uncertainty, percentage uncertainty will be equal to absolute uncertainty divided by the measured volume into 100, right? So absolute uncertainty is how much? Tell me. Zero
Zero
point
point 5.
0.5. 0.5. What is the measured volume? 25 and into 100, right? This will be the percentage uncertainty which you get, right?
Yeah.
Isn't it? So we
Yeah.
get the percentage uncertainty in this way, right?
Yeah.
Done this part? Okay.
Yeah.
Now they are saying that how the precision can be improved, right? Now you have to remember that there's a word called as precision. There's a word called as accuracy. What is precision? Precision is what? Doing the repeated trials and you're getting almost the same results, right? That is precision, right?
Yeah.
Suppose in a lawn tennis match, in a lawn accuracy and precision, right? What is accuracy and precision? Suppose in the lawn tennis you have to serve here, right? Now the person is serving here, right? Always is serving here. So it's a good precision, right? Understood? Good precision. But
Yeah.
it is poor accuracy. What is precision? Precision is that doing the repeated trials and you're getting the almost the same results, right? That is called as precision, right? Get my point,
Yeah.
right? Precision represents to the reproducible result, right? Right. So if you do in a series of trials with a high precision, the repeated values are very close to each other, right? Can you see this? This is the precise readings they are taking, right? And these are not precise reading, right? See, this is not precise reading. But what is accuracy? Accuracy is that if you have got a literature value of the result, right? If you got the literature value of the result, right?
Yeah.
Suppose the literature value of this result is 19.2, right? Is it clear? What is accuracy? Accuracy is the how close are the measurements to the actual value of a particular quantity. Did you get my point, right?
Yeah.
How close are these values to the actual value? Means literature value. See, this is precise. This is not precise. But both of these results are not accurate. Is it clear what is accuracy and precision?
Yeah.
Understood?
Yeah.
So if you see that when we talk about accuracy and precision, precision is the, it tells you the reproducible result, and accuracy tells you what? Accuracy tells you that how close are the measurements to the actual value or the literature value if you have. Now, accuracy, if you see that, we have to know the systematic errors. What are systematic errors? Systematic errors are those errors which are incorporated due to the wrong experimental setup, right? Wrong experimental setup, right? Number one. Due to faulty apparatus, right? Faulty apparatus we are using. Suppose you are using a thermometer, right? Which is by default always is recording plus 2 degrees centigrade more, right? Isn't it?
Yeah.
Suppose we are doing it 21.1, 21.2, right? 21.0, right? We are getting accurate result. But we know that the thermometer which we don't know that the thermometer which is using was not accurate, right? It was not, it was having a systematic error due to faulty apparatus, right? So actually, suppose the value is 19.1. See, it will be never ever showing you the accurate value, right? Why? Because of faulty apparatus. Did you get my point? Or wrong
Yeah.
experimental setup. Suppose you are doing the acid base titration and putting a temperature probe. Now you are not adding another beaker with glass full, isn't it? So what happens if you are not adding the glass full? The beaker, if you take like this, they'll be releasing the heat, and heat will be lost. So the actual temperature will be always on the lower side. Got it?
Yeah.
So to understand that how much systematic error is, what is systematic error? Systematic error is the error introduced due to the wrong apparatus or wrong experimental setup. We can
Yeah.
find out the amount of the systematic error which is there incorporated in an experiment by what? By the percentage error, right? What the percentage error tells us? Percentage error tells us the how to find a percentage error. Suppose you are doing acid base particular titration, right? The acid base titration, it should be around 55.8, right? Sorry, 57.8 for point 3, right? Now you're getting results like 55.8, right? Suppose you have not taken the glass full, right? Did you get my point, right? Glass full
Yeah.
to shield the heat, right? So you're getting a lower value. Can you find out that how much amount of the systematic error is there? Yes, we can find out by what? Percentage error. Percentage error equal to what? Experimental value minus the accepted value divided by the accepted value. Is it clear? Did you get
Yeah.
my point over here, right? Experimental value divide minus the accepted value divided by the accepted value, right? Got it? So
Yeah.
55.5 is the experimental value. What is the literature value? You can take literature value also. Literature value is what? 57.3 divided by 57 into 100. So percentage error will be telling us, indicates that how much amount of the systematic error are there in the experiment. Do you get this point clearly? So the
Yeah.
systematic errors are due to what? Examples: the beaker was not insulated, right? No glass wool was used. The reaction did not occur instantaneously, right? So the thermometer won't respond instantaneously. The concentration of the solution which you have which you have taken, right, might not be correct, right? Is it clear? Do you get my point? What is accuracy, precision, and systematic errors, right? Huh? Now, what do you mean by random errors? Tell me. Tell me, what do you mean by the word called as random errors? Random errors or random uncertainties are the uncertainties that is caused by the limitation of the measuring apparatus, which is beyond our control, right?
Yeah.
Isn't it? But you know
Yeah.
what? If you see that whenever we are measuring, suppose we are taking a 20 centimeter ribbon, and we are cutting down into 1 centimeter each and measuring it. So you get values like this. Can you see this? You're getting values like this, right? They're not same. Can you see this? Why? Because see, the when you're measuring, the inside the motherboard will be getting heated up, or there will be gush of wind, right, which is beyond our control, right? So it will be
Yeah.
giving you values like this. Now how to catch that? If a value is random error, random uncertainty, there will be values both side of the mean. Can you see this? This is the mean. Both side of the mean, it will be having values. Is it clear to you? Got it?
Yeah.
And how can you reduce the random uncertainties? Paper number 1B question. We can reduce random uncertainty by taking repeated trials and averaging this out, right? Because
Yeah.
they will be having both side values. So that will be averaging out, right?
Yeah.
Now, systematic error, if you see, systematic error will be always having values in one side. Is it clear? As I've
Yeah.
given the example, right? The thermometer was faulty. See, the actual temperature was 19.1. It was always measuring plus 2 centigrade extra. Understood? The values will be always one side of the mean value of the literature value. Did you get my point?
Yeah.
Systematic error, you can also measure the amount of the systematic error by the percentage error. Do you get my point over here? How to do it? Hmm?
Yeah.
Now you will be given questions like this. Yeah, I hope that you've seen the paper number 1B, that
Yeah.
how to multiply or how to divide, right? Suppose you have got values like this: 1.20 plus minus 0.01. You are suppose subtracting it from 1.08 plus minus 0.02, right? So
Yeah.
so now listen to this. When you're subtracting or you're adding, right? When you're subtracting or you're adding, what do we do? If you're subtracting or adding, the main value you have to represent at what? The main value you have to represent the answer in minimal decimal points. Is it clear?
Yeah.
When you're subtracting two values, which is having main value and the uncertainty value will be taken care next, right? But what you do with the main values? You have to keep the minimum decimal points. Is it clear?
Yeah.
Got it? Is it clear? We'll keep the minimum decimal points, right? See, minimum decimal points is how much? 1. So you have to represent this at what? 15.2. Got it?
Yeah.
Understood? Now, if you have to multiply two main values or divide two main values, how to represent the multiplication or the division result? By the minimum significant figures of these two values, right? Is it clear?
Yeah.
Get my point? So we are multiplying this by this. What are you getting this? What is the minimum figures? 3. So you represent this as 3 significant figures. Got it? Now come to
Yeah.
the part of the uncertainty values. If you see that we learned this percentage uncertainty is equal to absolute uncertainty by the measured value into 100, right? Isn't
Yeah.
it? So
Yeah.
so here you have to see that when we take two values, right, and we are subtracting or adding, we know that when you're subtracting, suppose the minimum temperature, maximum temperature, thermometer, right? We are subtracting, we get the delta T. This value you're subtracting, you have to represent this value in what? Tell me, minimum decimal points, right? Clear? So there are two
Yeah.
decimal points you represent. Now, whatever do with the uncertainty, whenever you are whenever you are subtracting or adding, the uncertainty values, what you do? Uncertainty values you have to add, right? And represent. Is it clear? So plus
Yeah.
minus zero point 0.04. Is it clear to you? This part is clear. This will be
Yeah.
coming in paper number 1B. Are you okay with this? Fine.
Yes. Yes.
You get my point over here. So this is the way we are doing subtraction and addition. Now, if you are having multiplication, right? Suppose I'm multiplying this by this, right? This by this. How to represent? Main values I told to you, right? The main value, what you do? You multiply and represent in what? Tell me. Minimum. Tell me. Significant figures, right?
Yeah.
Understood? How, what you do in this uncertainty values? What do you do? We convert this absolute uncertainty into percentage uncertainty. Is it clear?
Yeah.
Random uncertainty divided by the measured value into 100. We convert this, divide by the measured value into 100. We get this. Understood? We add up these two percentage uncertainty, right? Clear?
Yeah.
Understood? Then we multiply these two values. And what we do? We convert this total percentage uncertainty to total random uncertainty by the same equation. Percentage uncertainty is equal to absolute uncertainty divided by the measured value into 100. So
Yeah.
total percentage uncertainty was how much? This.
Well,
Measured value is how much? Multiplication. This. Got it? We get the total absolute uncertainty. Is it clear? Got
yeah.
it? This.
Yeah.
Is it clear? Now
Yeah.
we take this value. We know that we have to represent this in the what? We represent this in the minimum significant figures, right? Multiplication. See main value. So 3 significant figures, we do it over here, right?
Yeah.
Clear?
Yeah.
Understood? And after that, we are trying to keep the decimal point. See, this is the total absolute uncertainty we represent as this. Okay, this trick is clear to you. Fine.
Yes.
Understood this part?
Yeah.
Okay, can't fine. So
Yeah.
now this is the way we have to do it. How can you improve the precision? Uh, where is the answer key? Uh, okay, more reaction, right? Same as release. Just 1 minute. Okay. So how can you improve the precision over here? We can use a pipette, mainly pipette, right? Pipette will be better, right? We
Yeah.
can use a pipette, mainly a volumetric pipette will be better, right?
Yeah.
Because it contains graduation, right? Rather than the measuring cylinder. Can you go to the question again quickly? Go to the question again. So yes. So measuring cylinder, as I've showing to you also that in the concession when we're doing that, measuring cylinder will be having a huge systematic error, right? So always measuring cylinder, instead of measuring cylinder, always use what? Always use a pipette, right? Always use the pipette. If you're making a stock solution, always use a volumetric flask, right? So that will be better, right? Hmm. So they're saying this paper number one B, they're asking that suggest how the end point of the titration must be estimated. As I told you, that thermometric titration is what? We measure the temperature,
Yeah.
and after the reaction is over, so we'll be getting a graph like this actually, right? Not exactly we'll be getting the end point, right? So we go up this thing. By extrapolation of the graph, we can find out, right? State explain how the graph will differ if 1 mole per decimeter of sulfuric acid is used in this, right? Now tell me one thing, how will it differ? Tell me, we are taking H2, it's a good question. H2SO4 plus NaOH hmm, gives you Na2SO4 plus H2, right? So here what
Yeah.
happens? 1:2 ratio it will be reacting it. If you're taking HCl, right, it will be reacting it what? It will be reacting it 1:1 ratio, right? You
Yeah.
get my point? Over here, the same. If you're replacing it with the by the amount of the sulfuric acid, so sulfuric acid, what we are taking? If you're saying that 1 mole of HCl4 requires 2 moles of NaOH, right?
Yeah.
And here 1 mole of HCl will be requiring 1 mole of NaOH, right? On the alternative part, we are seeing that if you're adding the NaOH from the top, right? If you're adding the 10 NaOH from the top, right? 2 moles of NaOH will be needing for 1 mole of H2SO4.
Yeah.
And 1 mole of NaOH will be needing from 1 mole of HCl, right? So the
Yeah.
results will be the amount of the volume of the of the H2SO4, right? If you go in this way, right? 1 mole requires 2 moles, right? Here 1 mole requires 1 mole. So can you tell me that where will the volume used will be less to achieve the same endpoint?
Yeah.
Where will the volume? Tell me. Here adding 1 mole is neutralizing 2 moles.
Yeah.
So here 1 mole is even 1 mole. Got it? So the
Yeah.
amount of the acid required will be less over here to get the endpoint, right?
Yeah.
Is it clear to you? So it will be lesser, right? Is it clear? So we'll be
Yeah.
getting less. The half. Is it clear? Get my point? See,
Yeah.
half actually, right? Half. Why? I told you, na. It is diprotic, right? You get my point? So
Yeah.
this is the right answer. That almost half of the acid will be required. Because why? 1 mole is neutralizing 2 moles. 2 moles of NaOH. The moles is the same of the NaH you have taken, right? And
Yeah.
there 1 mole is required to neutralize 1 mole of NaOH. So the
Yeah.
volume of the acid will be almost required half. Almost half, right?
Yeah.
Smaller volume, better to tell half needed to require the endpoint, right? So that's
Yeah.
the thing we have to tell, right? The graph of the temperature against the titrate can be used to calculate the concentration of the alkali without knowing the concentration of the hydrochloric acid using enthalpy of neutralization, right? Explain how the concentration can be calculated. So what we do over here? We do Q is equal to mc delta T, right? This we do. Hmm. We know the delta T which is there. Mass of the aqueous solution we can find out, right? The NaOH volume you have taken add up to the volume of the HCl taken. Clear to you? We are getting the NaOH and HCl total volume will be the total mass of the water aqueous solution. C is 4.18. Delta T can be obtained from the graph which is there. Highest peak which you're getting of the temperature. Enthalpy of neutralization is 57.3 approximately. That is equal to what? Q divided by N. Q in kilojoules, right? We know the Q in kilojoules from here. We can get the
Yeah.
number of moles. We can divide Q kilojoules by 57.3. We get the number of moles. Once you get the number of moles, we know the volume of the endpoint, right? We are getting from the graph, right? The volume, right? Volume we know, right? V centimeter cube. So what we do? Number of moles divided by the volume of the HCl is what? Convert into decimeter cube. We get the concentration. That's the
Yeah.
way we do that. The heat change evolved to calculate Q is equal to MC delta T. I told you, no?
Yeah.
Then what happens? You know that enthalpy of neutralization. You have to know that 57.3. Then we use plug in that formula, and we're getting number of moles, right? number of moles when you get, we know the volume of the alkali, right? Which you have used, right? So we
Yeah.
divide by the volume, we get N divided by V, get the concentration. That's the way we do. Go to the next. Heat losses could make this process less accurate than pH probe. Outline why the thermometric method will always give you the lower, not a higher concentration, right? So what happens in the thermometric method? What is happening? You're having heat losses, right?
Yeah.
The thermometer won't be able to measure the temperature, right, due to heat loss. So what happens? Q is equal to mc delta T. Delta T we're getting. So delta
Yeah.
T will be less, right? It will be
Yeah.
lesser. So when we get the less delta T, what is this? Q in kilojoules divided by N is equal to delta H, isn't it?
Yeah.
So how do you find the number of moles? Q in kilojoules divided by the delta H, equal to number of moles. So number of moles will be lesser, right? It will be
Yeah.
lesser. Fine, it will be lesser.
Yeah.
Thus, we'll be getting what? We'll be getting a, this delta T is less. Why delta T is less? Tell me. Because there will be heat losses.
Yeah.
And the thermometer of the temperature won't be able to measure that amount, right? So
Yeah.
thus, you'll be getting a lower, always lower measurement. Suggest how the heat loss can be reduced. Tell me. I told you this thing just now of the uncertainty what we discussed. What we do? Tell me. We put it into a beaker. Tell me. And we put a glass full inside it, right?
Yeah.
Right? We put a glass full. This is the thing we have to know, right? We do put a glass full, right? State
Yeah.
one other assumption that is used to make the calculation of the heat produced. Tell me, what do you think? The assumption that no heat is lost. This is the thing you have to know, isn't it? If you have
Yeah.
to take into assumption what? Heat will be lost, right? Heat will be lost. Heat will be lost.
Yeah.
We take an assumption is what? No heat is lost to the surroundings. That's the assumption we do. See, you can use a insulated beaker or glass full also.
Okay.
So the assumption of what is it? No heat is lost in in the surroundings. Second assumption is what? The density of the solution is assumed at 1 gram per centimeter cube. And also we take that water has got a specific capacity at 4.18. The solutions which you take, that is also having a enthalpy of specific capacity of 4.18. That
Yeah.
these are the four assumptions we have to do.